Hello everyone, welcome back to the channel. So today we are going to solve the first practice problem on linked list. And we are solving Leetcode problem 876, middle of the linked list. So the problem states that given the head of a singly linked list, return the middle node of this list. So we have been given a list which is represented by the head, and we'll be given this head node as the input, and we need to return the middle node of this list. Now this particular problem can be solved using two approaches. First one is the more obvious or the more natural approach. So let's discuss this approach first. Now finding the middle cell in an array is pretty straightforward, and the complexity for finding the middle is big O of 1. So reason being, we can find the size of an array in big O of 1 time, and we can directly calculate the middle cell and jump to that cell again in O1 time. And because these cells are stored sequentially in memory and we know the exact address of the middle cell, we can return the middle cell in O1 time. But this is not possible in linked list because we might not know the complete size of the list, and we cannot jump to a particular node. Rather, we need to traverse the list from start, one node at a time. So the obvious solution here is to traverse the list twice. So let's assume that we have a list which looks something like this. So the obvious solution here is to traverse this list twice. So in the first traversal, we completely traverse the list and find the size of the linked list. So we start at node 0, and from here we go till the last node and we keep a counter, and we keep incrementing the counter in every iteration, so we'll get the total size of this list. In the second traversal, we keep a counter again, which is initialized as 0. So in our second traversal, we again start from node 0 and we keep a counter which is going to be 0. And at each step, we are going to increment this counter by 1. So when the counter becomes equal to, size by 2 minus 1, we return the value of that current node. So what does this represent? When our counter becomes equal to size by 2 minus 1, we have actually reached the index of the middle node, and from there we can directly return that node. So two things to keep in mind here. We could have avoided the first traversal if we would have stored an extra variable size in our linked list class. So the code for the linked list that we discussed in our introductory video, in that class we had an additional variable which has the size of the linked list. So in that case, getting the size of the linked list is an O1 operation. But for the scope of this problem, we can see that Leetcode has already provided as the structure of the node, and the input to our function is just a pointer of the type node. So we do not have a specific linked list class which has data members as the head or the size. We just have a head, and there's no way to store the size of this linked list. So in this particular case, we cannot avoid the first traversal, and we need to completely traverse the list to get the size of the list. The second thing is related to the traversal. Now we need to keep in mind that we should not use the head node or the input node for traversing the linked list. We should always make a helper node to traverse the linked list, because if we use the head node, we will actually lose the first node of the linked list, which is the head itself. Also, we would not be able to get the nodes already traversed, as there is no way to go back in a single linked list. So what I mean is that if we have this list, and right now head node is pointing to the first node. If we move this head node to the next node, there is no way we can get this first node or the nodes which we have already traversed, because there is no way to go back. Moving on to the second approach. This is also an elegant approach which comes in handy while solving other problems as well. So this is also known as the tortoise and rabbit algorithm. So in this approach, we try to find the middle in just one traversal. So in this approach, what we do, we maintain two variables for traversing the linked list. One is the slow and other is fast. So at every stage, slow moves by one step and fast moves 2 steps at a time. So now let's assume when slow and fast are starting from the same node or the first node of the linked list. So at any point, fast would have If fast would have traveled a distance x, then slow would have traveled a distance x by 2. Now at the last step, when x would be equal to the size of the linked list, or fast would have reached the end of the linked list, so x is equal to size, then x by 2 would be equal to size by 2, which implies that when fast reaches the end of the linked list, slow would have reached the middle of the linked list. So as soon as fast reaches the end, we can say that slow has reached the middle, and thus we found the middle in just one traversal, and we return the node being pointed by the slow variable. So the space complexity for both the approaches is big O of 1, and time complexity for both the approaches is big O of n, where n is the size of the linked list. So the time complexity for the first approach is actually big O of 2n, which is big O of n only. But for extreme cases where we are traversing a list made up of a million records, the second approach would give a slightly better runtime. But more or less both approaches are same in terms of runtime. So let's quickly go through the code for this problem. So this is the structure of the list node. So we have a val, which is basically the data stored in the node, and we have a next pointer, which is going to point to the next node in the linked list. So this is our method, middle node, which has received one input, which is the head of the linked list. So what we do, we initialize two pointers, fast and slow, and both of them are initialized as head. So fast will also start at the first node, and slow will also start at the first node. So in every iteration, the slow moves by one step, so it moves to the next node, and fast moves by two steps, so it moves to the next of next. Now, what is this condition? How did we decide the condition that we are checking here? So let's assume that this was our linked list. When fast and slow start at the first node, in this particular case, the slow will move by one step, but fast will move by two steps, and it will reach at this node, which is the end node. Now we know that slow is at the middle and fast has already reached the end node. So here our iteration should end. So this is checking the case where the next of fast is not equal to null. So in this case, the next of fast is equal to null. So we do not continue from here, we break from here, and whatever is stored in slow right now is actually the middle node. This first condition, fast not equal to null, is actually trying to define a stopping condition for the case where the size of the list is even. So let's assume that this is our list. So both slow and fast will start from the first node. When slow will jump to the next node, fast would have taken two steps and it would have reached there. In the next step, slow would have moved by one step, fast would have taken two steps, and it would have reached null. So in this particular case also, we have reached, the fast has reached null. So fast has traversed the complete linked list, and wherever slow is right now is actually going to be the middle of this linked list. So in this case, we do not need to iterate any further, and we can return whatever is being pointed by slow. So this second condition is actually defining the stopping condition when the list is even sized, and this condition defines the stopping condition when the list is odd size. And in the end, when we are done with this loop, whatever is stored in the slow is actually going to be the middle node, and we return it from here. So that's it for this problem. I hope that you understood the intuition and logic behind the rabbit and tortoise algorithm, and I also hope that you understood the solution for this particular problem. In case if you still have any doubts, please feel free to post them in the comment section, and I'll try to resolve them there. So with this, I think we can end this video here. See you in the next video. Till then, stay safe, keep learning. Bye bye.